near as scalable on their platforms as BFD. So we felt that we'd just take their advice and go with that. The limitations, or the things we can't replicate, is we couldn't replicate the flexible load balancing methodology whereby we can add and remove servers to the rotation without actually affecting existing TCP sessions on that server. So when we remove a route from the BGP ECMP rotation, we break all of the TCP sessions on that server and move them straight away, rather than letting those TCP sessions die naturally when the user is finished and move across. Now, we actually decided that these weren't required in our stack, and we were happy to sacrifice that functionality in order to implement this. So how do we do it? Essentially, a Twitter POP at a very high level has a couple of border routers, a reasonably large switching infrastructure, and a bunch of servers below it. And for obvious reasons, I can't go into much more detail than this, but the key thing to note here is we don't put the same number of servers under every aggregation pod, and we don't put the same number of servers in every rack. So if we were to start doing ECMP rather than through GRE tunnels on every switch in the path, we would end up with positions where a 5-server rack would have 1/5 of the traffic per server that a 1-server rack would, because we can't unequally balance on most commodity switch hardware. Also, we found that if we were to actually use our switches to do this, then most of the switch hardware we had didn't support consistent ECMP and didn't support wide hashes. There were limitations of 4 or 8-way ECMP. So the GRE tunnels came in handy to make sure we were able to ECMP in one location and also ECMP in a way that would work without breaking our stack constantly. The one thing we had to deal with in doing this, though, was that GRE pays a penalty on most commodity routers, on most vendor routers. So between different vendors, you're going to get between 1 to 2 passes through the ASIC that are additional for this traffic that you're going to have to pay the price for. Now, if you're outbound heavy and you're only doing this for inbound traffic, it probably doesn't matter, but it's definitely something we had to consider. And we spray our GRE tunnels quite widely across the ASICs in our routers in order to make sure that we're not stressing any one ASIC too hard. Also, a significant amount of policing is advisable here to make sure that if you're hit by a DDoS, your DDoS doesn't have 3 times the effect it might normally have on your router ASICs, which would be fairly bad if you're pushing your routers fairly hard. So the configuration we looked at on a Juniper, and I've picked the Juniper example simply because there's an interesting catch we discovered on the Junipers. Looks a bit like this, right? So nothing out of the ordinary in that we configure the ASIC to be able to support a GRE tunnel, we configure load balancing, and then we configure a GRE tunnel. The one thing we found in the Juniper use case is that to make consistent ECMP work, we actually have to configure the /31 GRE tunnel as a /32 with a mapped static route on it. We then, as you can see, accept the VIP routes in, but don't export any routes because we want to have a direct server return functionality, so we don't want the server to utilize any routes coming from the GRE tunnel for outbound traffic. So what were the challenges we ran into in doing this? The first one, which I'm not going to go into a whole lot of detail on as far as how Twitter implemented it, is that if you were to do this, you would need to be very conscious of the fact that you're now removing a state table that was in front of your servers. So you're going from a position whereby you're able to detect SYN floods and other attacks to a position where this is pushed to the server and the server must be able to sustain this. Now, by implementing a few kernel modifications, we've been able to scale this really well. And if you wanted to do this, a bunch of great information has been written on the blog post linked in the slide deck. The other challenge we ran into, and probably the biggest one, which stressed out Ali, who's sitting somewhere in the back, who works for Juniper, was that one of our Juniper had some real troubles getting consistent ECMP to work. So when we did initial testing, as you can see here, we sent 1,000 requests per second to 5 servers. We shut down only 1 server, and then we found that all 5 servers worth of requests went to a single server, which is obviously not desired because we've just torn down every single TCP session. And then we went back to distributing over 2 hosts, not 4. So we worked with Juniper, who were great at helping us with this, and managed to get a fix developed for this. And when we retested, you can see here that we actually have 40 different servers in rotation.